Okay. Hello, everybody. The subject of this lecture and the coming lecture will revolve about the particle swarm optimization algorithm. We have used PySwarm's library successfully to solve several examples, and we found it very useful and very interesting, especially because it also includes facilities to plot and to animate in two-dimensional and three-dimensional space. And here a question may arise: if we use PySwarms successfully, or we can use similar ready libraries, so why to go back and to discuss newly the particle swarm optimization algorithm? Really, this is because many people are not satisfied to work with PySwarms by considering it as a black box without knowing what is going inside. What is the essence of the PSO? Well, for those skeptic people, these two lectures, I think, will be very useful. I shall try to deliver the material here simply and precisely, without details, but hoping at the end you will be satisfied and you will feel that this is really the heart of the thing, and you can work with some confidence with PSO algorithm. Of course, we shall implement the PSO algorithm with a function of the test functions used usually, and I suggest to work with Rastrigin function because we did not work with it up to now, and really this function is specific and it is challenging to work with it with any algorithm because it has a large search space and it is a multi-modal function. So this function is a good example to be used to test the worked out PSO algorithm. And before working with it, I want to tell you that this is not a convex, non-convex function. This function has a number of local minima and one global minimum. So it is really a challenge to find the global minimum because many times some algorithms stuck at one of the local minima and they cannot catch the global minimum easily. This function was created at first by Rastrigin, and then it was also developed to be n-dimensional. In most cases, we use it as a two-dimensional function, and the minimum for any dimensional value will be always equal to 0. The bounds of the variables are between -5.12 up to +5.12 for any number of dimensions. Well, I want first of all to plot this function for you to show you what I am saying that is true. And after that, I shall try in this lecture to familiarize you with some basic functions, Python functions, which are used in building and in analysis of the particle swarm optimization algorithm. In the coming lecture, we shall work with the PSO and Rastrigin together. So let us try to plot this function. As usual, we import the required libraries for this purpose. Because we want to plot, so we need matplotlib library, mathematical plotting library, as PLT, this is alias word for it. And also we import the axis 3D here method, because we want to draw or to plot a three-dimensional space. Yes. Color map, here we import also the color map module so that we can select maybe the most appropriate color, or depending on the taste of the designer. So at first we define the x-axis as an array by using numpy linspace function. Here we included or passed the bounds of the function -5.12 plus 5.12, and we are asking the linspace function to facilitate 100 points, separated equally, of course. The same thing we do with the y-axis, and because we are working with a two-dimensional function and we want to plot it to see it in 3 dimensions, so we use the numpy meshgrid function. Now we have converted the xy one-dimensional arrays to another xy two-dimensional arrays. The z variable, which represents the third dimension, is expressed here as a two-dimensional function with x and y. Of course, we can write x1 and x2. It is the same thing. We create the object of figure by calling figure function from PLT, and we added to the figure the axis and passed to the axis the word or the keyword projection 3D, especially to have a 3D axis. Now we can use the plot surface function of PLT. We pass there the 3 coordinates, x and y and z. Yes, rows stride I gave it 1, and the column stride I gave it 1. You can put any number desirable. The color map is given here as NiPi spectral, but you can use another types, like for example the plasma or cbdes or rebdes. It depends. Yeah. After creating or plotting this function, we save it by using the save figure function and have given it a name, Rastrigin graph PNG. So everything is ready. If we now run the program here in the notebook, we shall get the figure. Again, here is the figure of the Rastrigin function. As you see, it has a lot of local minimums, and as the figure shows here, the global minimum will be around 0 here in the Z region. But really, it is not that clear. I want to show you a better plot. I have taken it from literature so that you can see the global minimum also. I put it in the pictures for you. And it is called Rastrigin CGR. Here it is. Double click it and I open it. Look how it is clear, a really model function, and the global minimum is exactly at x equal to 0 and y equal to 0. And the value of the function is equal to 0. So I think now we know with a good background what is the Rastrigin function and how it looks like. For you, I have redrawn it by using the red gray color map here with the number of row strides 10 and column strides equal to 10. And I have kept the other things constant. I didn't change anything here, but I do not like it. I just wanted to show you. Here's also another plot by using the Viridis color map. I think this is not the most important now, but it just to show you these things. So now we know our function which we are going to work with. And as I told you at the beginning of this lecture, I want firstly to illustrate to you some short but interesting functions which are used for building the PSO algorithm. Remember, when we worked with the pi swarms, for example, we only decided the number of the particles and the number of iterations and some of the constants like the acceleration constants C1 and C2, or the learning constants C1 and C2, and the weight or inertial constant W. We did not create the swarm itself. It is created automatically by the program. But when you will work with PSO, you have to create it yourself. And usually it has a number of particles, and this number of particles is represented as the number of rows in a two-dimensional array. And the number of the columns here represents the two XY positions of each particle exactly. So how to create the particles of the pi swarm. And in addition to that, how to create the initial values of the velocity, of the velocities of the pi, of the particles of the pi swarm. Let me first show you how we do it with the particles themselves, how to create the array which represents the particles. We use for that numpy, random module, and uniform function. So we import numpy as np. We decide the number of particles which we are going to work with. Normally, as I told you, 10 to 20 to 30 to 50, it's always good, no problem. And now we need to know the bounds of the function which we are going to work with so that the created particles will be within the bounds. Here, as you see, we have a list here with 2 zero values, which represent really the minimum or the smallest values of x and y, x, y minimum. And the maximum value of x is 10, and maximum value of y also is given 20. It could be, of course, 10, but it depends. This is just optional now. So we are using the limits of the function here. And now we use the uniform function, numpy, random. We call the random, then we call the uniform function. And this function now, in this function, we pass the low limit, low, which is equal to xy minimum, and high, which is equal to xy minimum, which are these two lists here. And the size of the particles, the swarm. The size is equal to the number of the particles, which is 10 here given, and 2 represents the positions which we will work with, 2 positions. If we will run the program, we shall get 2 columns, x and y, and a number of particles up to 7, up to 10 here, not 7. In order to just make it easier, I have rounded the floating number here to the first 3 values. So np round the data, which is already existing, to 3 digits, and I have got these 2 columns with 10 rows representing the particle. When we really, the particles represents the swarm here in this case. The particles with S, of course. Okay. Sometimes, with this example here, as you see, 0 and 10 here, the minimum value for x is 0, the maximum value is 10. Here the minimum is 0 and the maximum is 20. So the x range is different than the y range value. The values of x are different, have a different range, or within a different range than the y values. But if you want them to be the same, it is easy. You can write here 10 and here 10, as you did here 0 and 0. And then we can say that the limits for both between 0 and 10. So here, in this example, I selected the number of particles 10, and I have used the random uniform function with the low value. Now, here it is equal to 0, and the high value is equal to 20, for example. So because it is randomly selected, now it could be between 0 and 20, it depends. And the size is n, which is 10, and 2 here for x and y. So the values here, if you examine the values, are really between 0 and 20. Here we have a 17, for example, here 16, here 17, and here also we have 18, 10, 11, and so on. So it depends what do you want, and I think which decides this approach is the values of the bounds of the optimized function. When creating the PSO, also we need to create an array which represents the initial values of the velocities. For the velocities, here I mean every particle will have its velocity. So this will be an array of values representing the velocities. The most important thing is here the dimension of the created array must be exactly the same dimension as the dimension of the particles, because every particle will have a specific value of this velocity, so they should have the same dimension. For this purpose, it is recommended to use NumPy zeros-like array function. Here, how it works. We import NumPy as np. I have created an array, just optional array, by using a range function beginning from 0 to 5. The data type I gave, it is integer. Of course, it could be floating. And I have reshaped this one-dimensional array to two-dimensional array, 2 rows and 3 columns. Here it is, as it begins from 0 to 5, so 0, 1, 2, this is the first row, and this is the second row, because it is 2, and 3, 0, 1 element, 2 elements, 3 elements. So this is the array which we have created here. But we do not want these numbers. Really, we need to create an array with zeros. Of course, it is not a must to have always initial values of velocities equal to zeros. You can have any other values, any random values, but it is also used. No problem with that. So here we use, or we implement the NumPy zero-like function. We imported NumPy. From it, we called zero-like. This is a function. We pass to this function only the name of the function which was created for the particles, so that to have its dimensions, the same dimensions, which is 2 to 3, 2 rows and 3 columns. So as you see here, this function which was created firstly, which represents a particles array, is passed here with a data type integers. I have written here shape equal to 2, 3. This is just to remind you with that. So we now have a variable called myArray, and this array will be zeros with 2 rows and 3 columns. Here it is, myArray, zeros values all, 2 rows and 3 columns. This is considered as initial values of the velocity. Of course, here I wanted also to show you that we can do this by using directly NumPy zeros. I can call from NumPy the function zeros, And within the function, I have to define the shape of the array, which has 2 rows and 3 columns. Here I have to define it. And as I told you, it should be exactly the same as the particles array shape. And if you print, I call this array as Jamal, for example, and if you print it, you will get exactly the same answer. But there is a difference between both, that here you guarantee in advance that it will have the same shape as the particle shape. Here you have to remember that and to write it here, otherwise some problems will arise. Okay. Now we have created the swarm, and now also we have created the array representing the velocities of all the particles of this swarm. Here also, I am giving you another example and tying it with the bounds of the objective function. Suppose we need to establish or to create or initiate a swarm with 7 elements, 7 particles. Number of particles, this is a variable, and we assigned to this variable number 7. NP array is called bounds with a lower limit -5 and 5 and upper limit -5 and 5 also. This list here and this list here, which are included in this array, usually are taken from the data representing the objective function. Yes. Now, if we take this array, which is called bounds, and we extracted from this bounds all the rows and the first column, we will have the following. First of all, before doing that, if we print the bounds here, print bounds, if there is a bound, yes, print bounds here. No, I have printed it, bounds. It should be, it is this, no, it is this shape here. The bounds here, this bounds, print bounds here, print bounds, which is bounds. This array with the title bounds is 2-dimensional with 2 rows and 2 columns. This is the original array. Now, if we extract from it all the arrays, all the rows, we have 2, and the 0 indexed column, we will have -5 and 5. We will extract this -5 and 5. This represents the low values of both arrays, of both particles. If we take the bounds, all rows with the first index 1, we will have 5 and 5. This 5 and 5, we will have them here. The array, which is called bounds shape, it has a shape 2 by 2. 2 arrays, 2 rows, and 2 columns. If you look here now, particles variable, we create the particles now, NP random uniform, as we did before. Here, for the low bounds, now we took the bounds and extracted from it all the rows and the first row, which means -2, -5, and -5. And here the bounds with all the rows extracted and the first column, which is 5 and 5. This is the lower bounds. This is the upper bounds. Number of particles is known, which is 7 here. And the most interesting here, the dimension of the array. And the dimension here is shown as bounds, not shape of 0. What does this mean? The shape here of the array is equal to 2 and 2. So if you extract the first element, it will be 2. So instead of bounds dot shape of 0, we can write only 2. But this is more generic and more common expression. So I kept it as it is and explained to you how it comes and what does it mean. So this means that we have a particle, a particle with number of particles equal to 7, and the positions or the dimensions are equal to 2. Yes. Okay. Now we did this. If we print them, we shall take, of course, these 2 particles. Why there are 2? Because really what I have done here, as you see, I created the array and created the particles, and I printed the particles. Then I gave it another name, particles 1, and instead of -5, this expression, I used -5, and instead of this expression here, I used 5, and I put the number of the particles 7 and the number of dimensions 2, and you expect maybe that I shall have the same particles here and here. But if you examine the values here and the values here, you will find them different. Why this difference? This difference not because of any error in this expression or in this expression. This is because when we run the random function, for every time you run the random, you get a random value. So here we have a random value, and after a while, when it is run again, we will have another random value. So if you want to create particles with the same values, you need to either to make a copy of one of them, to make the other the same, or you need to use what we call the seeds method, with which we can guarantee that the random module will give the same values every time you run it. How we work with this, we shall demonstrate this to you also or through an example. Okay, let us do it. So here in this example or this paragraph, we create randomly 2 arrays. Two arrays with the same elements values by using the default random number generator. The default random number generator. Of course, and by using the seed value which we want. And now I shall explain to you what do we mean by it. So as a beginning, we imported the NumPy library as np. We have defined the number of rows and the number of columns of our particles as usual. Now we have created a random number generator, random number generator, with a specific seed. So what we have done, np, we call from numpy random, and from random we called default rng, and we passed through it seed equal to 42. Really, number 42 is not a magic number. You can write, instead of 42, 20 or 10 or 15 or 100, any number you want. But the software of the random function really is not exactly means random. So if you put the seed equal to 10, you will get random values here, but only for the value of 10. If you put number 14, you will get for the number of 14, 42 for the number of 40. This guarantees for you that you will get the same values of the elements of the array when you run the random value, but these values will be created randomly. Okay, so RNG, random number generator, now known to us, we call from it random and pass there the number of rows and columns you need. And now we will have the random values, and these values represent an array. Okay, so these random values here are assigned to an array. I call it array 1. And also the same random values, I assign it to array, I call it array 2. Okay, now I want to round array 1 to 3 digits, np.round array 1 colon, apostrophe 3, and np round array apostrophe 2, 3. This is array 1, this is array 2, but both of them will have a rounded figures up to the 3rd digit. So now when I run the program, I shall have array 1 and I shall have array 2. They will have the same elements and both will be rounded to 3 values. If you look here, this is array 1 when printed, this is array 2, but this is the element, this element has the same value as this element. This element dot 45 is the same element here, and so on. So I have created 2 arrays randomly with the same elements values. Can I select them randomly with different values? Yes, I can. Instead of 42, for example, here, let me put 20 or any number. 33, for example. Now, if I run the program, I shall have also it seems some problem here, and seed method, where it is, and seed random lab generator, random yes, the problem here, look, here there is no hash, so I have to put a hash so that not to consider this line, and that's it. Here I have to put a hash here, and everything will be okay. Now if I run the program again, look, here at dot 44, dot 44, dot 343, dot the same typical exact array, but with newly selected random values. Also, I have an idea here. If you do not need to work with this approach here, You can create the first array and made a copy of it. We have made array 1 by using random values which were created here. So I can take array 1 dot copy function and print it, and I shall get exactly the same. So these 3 arrays have the same size, I mean the same number of particles, the same number of positions, and the same values for each. As you see, these things are necessary to understand in advance before working with the PSO. I am not sure that all the listeners here have a sufficient background in Python, so I am trying to explain to you these things before working with the PSO directly. Here also, I want to give you a short introduction and definitions of some expressions which I am going to use and which we use usually, because maybe it seems to you not understandable when working with the examples. So first I am talking about fitness function and the argminimum function. The word fitness, sometimes it represents the goodness also, and the minimum, the minimum or the argument of the minimum value here, function. These functions are used also frequently in PySwarms. When we talk about a fitness function, simply let me tell you, the fitness function could be any function, but while working with PSOs, we usually use the same objective function to find the fitness function. The fitness function is the same objective function, but with substitution of the values of the coordinates of the particles in the expression of the objective function. So fitness is a function that takes particles' position, as I told you, representing a potential solution. What does it mean? Because the position of each particle is the solution, intermediate solution, which is going to be improved and improved until we come to the last iteration. So this coordinates of the I particle are put inside the objective function. As a result, we get a value. This is called the fitness of the function. Yes, it retains a single numerical value, which retains the objective function. When you substitute there the variable with the xy, you will get the fitness, which is normally a number. It represents the quality. Why it represents the quality? Because this value shows you to which degree this particle position is nearer or closer to the optimal value. For every particle, there will be a position. This position now is mapped to a value. This value represents to which degree we are close to our minimum. In other words, fitness evaluation, now it is called, each particle's position is evaluated using the objective function and resulting in a fitness value or a cost value. I hope that this is understandable by you. What do you mean by personal best? pbest. Personal or local means the best position taken ever by each particle. Each particle memorizes its positions and the position which is the best relative to the optimum value is called pbest or personal best. Each particle maintains its better ever position, personal best or pbest, and its corresponding fitness value. Because we are talking about a position and every position has a fitness, so we have pbest position and we have also a pbest fitness for each particle. Now, among all particles together, we find a particle that has the best position relative to the optimal. This is called global best, gbest. The swarm keeps track of the best position found by any particle. So when we talk about the global best, this is the best position of one particle among all other particles, which is closest to the optimal value. And of course, because you are talking about a global position here, just best global position, so there is also a global fitness. So we have, and we shall meet with these expressions in the future, maybe in the next lecture, where we shall talk about the position and the pbest and the best fitness and the global or gbest, global best position, and with the global fitness. Okay. In each iteration, as I have said, the initial position of any particle is not stationary. This algorithm works dynamically from one state to another state, from one iteration to another iteration, and by moving from one iteration to another iteration, the particles change their positions, you see, and at every iteration, the fitness function is applied to each particle to determine its fitness. So every iteration we have, at every iteration, we have a p-best and we have a g-best. The fitness function could be objective function itself. This is clear. I have told you about this. A lower function value would indicate a better solution. Why? Because we are talking about optimization for finding the minimum value. If we are targeting the maximum value, so the fitness should be the highest value will be the best. PSO keeps track of the best solution found by each particle or pbest and the best solution found by the entire swarm gbest. I hope that this is also understandable by you, but if you feel a little bit confused, you please go through it once and twice, and I am sure you will get the inner meaning of it. Okay. Now we have a swarm which is composed of a number of particles, n particles. The argmin minimum function, this function, which gives you the index of the minimum value within the array, argmin minimum function, plays a crucial role in identifying the best performing particle within the swarm. What does this mean? We have a swarm. We have a number of particles. Every particle of these particles has its coordinates and its fitness. The fitness is numbers. How to find the one which has the best fitnesses? We use for this purpose argminimum. Why? Because the particles are represented as array. And this array, by using the argminimum, we can define the index of the particle which has the minimum value. This is the idea. Okay, so each particle in the swarm represents a potential solution to the optimization problem. Okay. A fitness function is used to evaluate how well each particle performs. Good, now we know this. This function assigns a numerical value representing the goodness of the solution. We know that. So all these expressions now well known to you. Now, finding the best local position, here we mean by that the best position for a given particle. Each particle keeps track of the best position. It remembers its position it has encountered so far, which is known as its personal best or pbest. This is some kind of repetition I am doing here. Now, we come exactly to our function. The argminimum function is used to find the index of the particle with the lowest or highest, if we are targeting the maximum value, fitness value, among the current pbest positions of the swarm. So we have a lot of pbest values. We want to find the gbest, the global best. We use for that the argminimum function. Yes. Finding the best global function, the argminimum function is also used to find the index of the particle with the lowest or highest fitness value among all particles. So I think this is also known now to us. These definitions now, I hope that they are understandable by you, but will be used with the same content and as I meant here in the next lecture. Let us see again through an example how we work with the argminimum function. Import numpy as np. This is an example. I have a list here and I created an array from this list. It is called arr. And now I want to find np argminimum of the array. I want to find the index of the minimum value here. These values are similar to the values which we have as fitnesses. Which one of them here with the minimum value? We find the index of the minimum value. The minimum value here is number 1. The index of this one is here 0, 2, 3. So 0, 1, 2, 3. It is 3. The index of 1 here, the position is 3. So the argminimum function gives me 3 here. If I print, of course, now I arrange it as np argminimum of the array, which I have created. I assigned it to a variable called minimum index and printed it. Now print minimum index. When I print the minimum index, I will get here number 3. Minimum index is equal to 3. Now, in Python, if you know the index of a number here, you can define its value also. You can pass the value of the index here in the array, and you can find the minimum value here, which is 1. So minimum value of the array with the index minimum index here, which is, instead of it, if I can write 3, it is the same. And array of 3 will give you 1 here, which is the minimum value of this array. So as you see, we use the argument or argminimum function in order to define at first the index of the value which is minimum within the array, normally the array of fitness values, and at the end we can find the value of the minimum itself, the minimum fitness value. Here is another array 2D, I call it, two-dimensional. So I create here, as you see, this is a list, another list, 3 lists, an array of lists here. I shall have 3 rows, yes, and 3 columns. So this is the array which I have 3, 1, 4, and 1, 5, 9, and 6, 2, 5. This is our array. Now it is printed. Now this is not a one-dimensional array, 3-dimensional array. The argminimum function makes it possible for you to find also the index of the minimum value if you traverse the rows or if you traverse the columns. The rows have an index equal to 0, axis equal to 0. So if I want to traverse the rows, which is equal to 0 here, I have to go through this column. The minimum value here is 1, which is 0. The index of it is 0, 1. So it is here 1. The answer is 1. The other column here, the minimum value is 1, which has an index 0. This is 0. The third column here, the minimum value is 4, which has an index 0. It is 0. So these are the indexes of all the minimum values of the rows. If I want to find the indexes of the minimum values by traversing the columns, horizontally moving, I have to write here 1 instead of 0. Axis equal to 1. Now, if I go by this row, the minimum is 1 here. Its index will be 0, 1, so it is 1. The minimum in the second one is 1. Its index is 0, so it is 0. The third row, the minimum is 2. Its index is 0, 1, 8, 1. So 1, 0, 1 is the array of the index, the array of indexes. So as you see, this is a very powerful and a very useful function, and inevitably we shall face it when working with PSO algorithms. Okay, let us look at this example also. We have imported NumPy. We have created an array. This array is one-dimensional, as you see. NP argminimum array, we want to find the minimum index. The minimum is 1 here, as you see. Its index 0, 1, 2, 3, 4. So the answer will be 4. This is it. And now, if you want to find the value, we substitute the value of the index in the array, and we can find the value itself, which is 1. So I think there is no problem with this. Another interesting issue, which we also face in the PSOs, is the enumerate function. The enumerate function is a Python tool that allows you to look through an iterable. Iterable means a list or an array or a tuple, like a list, tuple, or string, and have access to both the index and the element itself. What does this mean? Let us also understand about this function through examples. We imported NumPy. We have here, as you see, a list of strings. We called it data. And we have another list of numerics. We called it values. If we write list, this is list now instruction, enumerate the function of values, we get the enumerated data. If we type this enumerated data, we will get the following. What do we have here? A list? Yes, we have a list. All the strings which are here, each of them has an index. The index of this one is 0, so it is 0, and coupled with 4. Now it is a tuple 0, 4. The index of banana is 1. It is coupled with 2 as a tuple 1 and 2. And as you see, the last one, of course, they should have the same number of elements: 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And at the end, we will have the last string here, which has an index 4 with the value of 5. This is the enumerated value, which means that we are pairing the indexes of the first list with the values of the second list. Another example. Now we know what does it mean. What is enumerated data? Here we have also another list, a list of strings. For I, this is variable, names in enumerate of I, print I names. You will working as a for loop, looping through the elements, but giving them indexes. The first one is given an index 0, 0 gigs, 1, 4, 2 gigs. This is the facility which is given here that allows you to loop through the iterable like a list. Okay, let us also look at this example here. Import numpy as np. This is the list named data, another list names values. We have, I think, passed like this. We have composed or made an enumerated data of it. So we will have 0, 4, 1 here, 1, 8, 2 with 3. This is the enumerated data. Now we can use our function np argminimum of values here. These are the values. The minimum value is 3. So the index of it 0, 1, 2. So if we give this expression a name called minimum value of x and we type it, the minimum value of x will be number 0, 1, 2, will be 2. Here it is, minimum value index is 2. And of course, if we substitute it in the values, we will get the value of 3, which is here 3. Okay. The last issue I am discussing with you today. np.where function. The syntax of this function, now we call it from numpy, where between two brackets, this is a conditional case, and this is an array, and this is another array. The X array from which we choose the variable when the conditional case is true. The Y array from which we choose the value when the conditional case is false. Sometimes also we do not have the array X and Y, but we have only the conditional case. Here, in this case, we can find the index of the array where the condition applies, where the condition is true. How? Let us explain this to you. Import numpy as np. Okay. We have created an array. Now, this is the array from which we take high if the conditional case is true. And here we take low if the conditional case is not true. The conditional case here is the array more than 20. Here is the array. We have cases where it is more than 20. In this case, it is less than 20, so we take low. Now we have the result low. It is equal, so high. More, high. Less, low. Higher, high. This is the result, as you see, with the existing high and low arrays and the conditional case. But the most interesting here is this case. Here, this is the most interesting. NumPy where array more than 20, and we do not have high or low. So what do we have here? We have this array, our array only. The array is more than 20. When the array more than 20, it is true. When it is true, we have to take the index. So this is false. We do not take the index. Number 25 is true. It's indexed 0, 1, so we have 1 here. Number 30 is true. So it is 2, we have 2 here. Number 40 is true. 0, 1, 2, 3, 4, so we have 4 here. So this is the case which we usually face when working with the PSO. Okay, I have tried to explain the things as I could. The examples, I hope that they will also help you to understand it better. You can refer also to literature to know more about if you are not satisfied. But these things are necessary to understand and to be aware of before working with the particle swarm optimization. This subject will be discussed in detail in the coming lecture. Until then, I wish you the best, hoping that you will have a happy day. Thank you for listening, and goodbye.